Good day everyone, and welcome to the next module, Module 7, Pesticides for Fall Armyworm Control. We are going to hand over to Mr. Mark Edwards, who is the Consulting Entomologist at Villa. Mark, over to you.
Thank you, Nalene. As you've heard Nalene say, we're doing the last module that we prepared in this project on fall armyworm mitigation. And today we're going to look at the actual pesticides that one can use for fall armyworm control. As you might have realized from all our previous modules, we've done some work on biology, we've done some work on non-chemical control methods, on scouting for fall armyworms. And the reality is that people in Africa are, because of this new pest, are going to be using pesticides. So what we as a project and what you as trainers and people involved in fall armyworm projects in Africa need to do is make sure that people who are going to use pesticides use them correctly. There are many governments in Africa who have been purchasing pesticides and giving them away for free to farmers to combat fall armyworm. And what we'd like to make sure is that those farmers that receive these products as well also use them correctly. So what we'll discuss today is, briefly, I'll talk a little bit about the hazard and risk of pesticides, because pesticides are designed to kill. They're designed to kill insects, but because insects are living organisms, they can also be hazardous to non-target organisms and of course human beings and their livestock, etc. Also, we'll discuss briefly insecticide resistance, which is a major issue with fall armyworm all over the world where it's found. We'll also discuss the pesticide label, because if one's going to be using a pesticide, one must be able to understand what the label tells one to do. And then, of course, because people will have a choice of pesticides, we'll also briefly discuss how people should go about making a choice of insecticides. I think everybody can recognize that a shark can be seen as a hazard. A shark is never going to be a risk to any human being unless you go and swim in the ocean where the shark is. And I think most people have heard of the movie Jaws. So this illustrates it very nicely. There is a hazard associated with any pesticide because, as I said, they are designed to kill. They're designed to kill pests, not humans, but of course, because our biology is similar, they can also affect humans negatively, and of course other organisms in the environment. So as a trainer, one can use these type of images and these type of stories about that people recognize, things like the Jaws movie. I think most people are familiar with it, to illustrate these various concepts to farmers and to make them aware of the fact that there are these issues around pesticides. So what I've illustrated in this slide, and which you can then discuss with farmers, is this pickup truck a potential hazard? And one would like to get feedback from the audience on these types of questions. And the type of answers one can get is, yes, of course it's a hazard, but it will never become a risk unless you actually drive the pickup truck. And here you can see somebody, of course, using their pickup truck to drive around. And of course, there's some traffic on the road as well. And I think that the type of questions to ask farmers and people who are being trained about fall armyworm is, how is this a risk? And what are the factors that can increase the risk associated with using this pickup to transport my cow around? And the types of things that one can look at is things like, does the guy even have a license to drive the vehicle, for example? Other things are, what is the condition of the road? Is he driving at nighttime or not? Is it raining? What do his tires look like? Are they in such bad shape that he's increasing his risk? And by using these kind of examples, one can lead trainees and farmers to a realization that although a pesticide is inherently a hazard, things that the actual farmer or applicator does can lead to increased risk once using the product. So in some of the slides you'll see further along today is we use this pesticide, Edition 150 SC, as an example when discussing pesticides for fall armyworm control. It is a registered pesticide in South Africa for fall armyworm control. That's why we use it as an example. And as I said, any pesticide, if it's in a bottle like that, is a potential hazard. Only once we use the pesticide does it become a risk. And here you can see a little icon of a farmer with a knapsack sprayer, hopefully spraying his maize for fall armyworm. And what he does, and what he does correctly, mitigates that risk. What he does incorrectly increases the risk associated with using that pesticide. You will see in some of the materials that we make available on the website, and at the end of this presentation you will see a link to the website where all these training materials have been deposited. You will see slides in the presentations that have a blue text. These slides are not intended to be shown to trainees or other people that you're speaking to about fall armyworm, but are used to alert the trainer to do certain things or talk about certain things to the group that he's presenting to. So just to alert you to the fact that we have these slides in between that will actually get you to interact better with the audience that you have. So here, for example, is one where we say we want the participants, this is now the trainees or the farmers, to list any actions or circumstances that will increase their risk while using a pesticide. And one will get a variety of answers which one can then enter into a discussion with, and which one can always link back to materials in, for example, Module 1, where we talk about the responsible use of pesticides. A lot of these issues and circumstances, of course, link between the various modules that we've prepared. So, how can one increase the risk when spraying with a pesticide? And this is just not an exhaustive list, but this is something that probably the farmers might come up with themselves. And I'm not going to discuss the list. You can go through it and then discuss these issues during training sessions. Of course, the risk of a pesticide is linked to its toxicity. So if myself as a company decides to develop a new insecticide active ingredient for fall armyworm control, one of the things we have to do is research its toxicity to find out how toxic this material is. And this is to do with the actual registration of these products in different countries, because nobody wants to register a product in a country that is very effective on fall armyworm, but at the same time is adversely affecting the environment or the operator or applicator or spray person's health, or the health of other individuals, or the health of animals in the environment. And to do this, a company will take a rat, which is the normal experimental animal is used, and we will feed this active ingredient to the rat, or expose the rat to it in some other way. In other words, on the skin or on the eye, or almost force the rat to inhale the substance. And this result that we get from the rat then acts as this model organism, so we can extrapolate this result from the rat, which is a mammal like humans are, to human beings, and in this way decide whether the active ingredient is contributing in some way to control and not causing so many adverse effects that we do not want it being used in the environment. Next. So there, like I already spoke, there are different ways of doing this. We do it orally, in other words, feeding the substance to the rat. We do it dermally by applying it to the skin, and we do it by inhalation, by getting the rat or the target organism to breathe in air in which this active ingredient is present. There are other toxicity measurements that are looked at, and if I can have the next slide, please, we'll look at those. So we look at things like teratogenicity. Does this active ingredient affect the unborn fetus? We look at carcinogenicity. So does this active ingredient cause cancers in animals? We look at eye irritation as well, because eyes can be very sensitive to pesticides. We look at skin sensitization. Those of you who've worked with pyrethroids will know that if you spill pyrethroid on your exposed skin, it gives you a burning and itching sensation. We also look at the reproduction, whether the pesticide affects reproduction, and then what we call mutagenicity. Does this active ingredient then cause mutations in the genes of the animal? So all these things are researched before an active ingredient is released into the marketplace to control, for example, fall armyworm. How do we measure that? There's a measurement that's called the LD50, which stands for the lethal dose of the active ingredient that will kill 50% of a population that is tested when it is fed or exposed to that population. And it's usually quoted as the LD50 per kilogram of body mass. And how do we explain that to the trainees and farmers? If the LD50 for a product is, for example, 55 milligrams per kilogram, it means if we have an animal that weighs 1 kilogram and we feed it 55 milligrams of that product, it will then kill 50% of that group of animals. But if the animals that we're testing all weigh 10 kilograms, then we would have to give them or feed them 550 milligrams, 10 times as much, in order to kill 50% of those animals. And this is the way in which we test pesticides before bringing them to market. What one also has to realize is that it's never the active ingredient that a company will sell to a farmer to control fall armyworm. It would be a formulation. So the toxicity of the active ingredient is not necessarily the same as the toxicity of the formulation. And when one goes and looks at LD50 figures, one must just realize that the higher the figure, the less toxic the product or the active ingredient is. As an example of the difference one can see between active ingredient and formulation toxicity, this is just an example of an active ingredient that's LD50 is 139 milligrams per kilogram. Once one formulates it into different formulations, like a ultra low volume, emulsifiable concentrate, and the others listed there, the LD50 of that formulation itself changes drastically. And in some cases, it can be as drastic as from changing from 139 to 40,000, which is a huge difference in toxicity between the active ingredient and the formulation. So one must not assume that because an active ingredient is very toxic, the product that is being sold is necessarily as toxic as that. And this is something people sometimes forget. So how does this compare to, let's call them natural substances? As I've stated already, we measure this as milligrams per kilogram body weight for the LD50. And there's an active ingredient called aldicarb. Many of you will probably remember it as a product called Temic if you worked in agriculture for a long time. And Temic's LD50 was 1 milligram per kilogram. And because I worked for the company that sold this product, that, to my knowledge, is one of the most toxic active ingredients amongst all pesticides. It's now banned in most countries because of this toxicity and because people basically misuse the product. So it's not really available anymore. But if one compares this to natural, call them poisons, not pesticides, one can compare it to something like Progonomyrmex harvester ants that are found in the United States. They sting just like bees and wasps and so on. And their venom has an LD50 of 0.12 milligrams per kilogram when tested in mice. So you can see it's an order of magnitude more toxic than an active ingredient of the nature of aldicarb. So there are many chemical substances in our environments that can be as toxic, or of course also a lot less toxic than what pesticides are, and one must remember that too. And despite all the precautions that we've discussed, for example, in Module 1, it is possible that people will always get exposed to a pesticide. What do we do in that case? And this is something one has to be very strict about with farmers and people using pesticides. One must immediately remove all clothing that has been contaminated with the pesticide. You then wash any of the affected skin area thoroughly with soap and clean water. It's very important, if the eyes have been affected, to wash them in clean running water for at least 15 minutes. And if the exposure has been serious, one would always recommend that one takes such a person to the nearest clinic or doctor to make sure that he's okay, or she is okay. And what we normally also recommend or require is that one takes the label of the pesticide with, so that the physician can understand what has happened in terms of the active ingredient with this person that's been overexposed. Something that we find very interesting as manufacturers and people selling pesticides is what happens when somebody has been exposed. Or something else goes wrong during the pesticide and somebody has now been overexposed to pesticide. What we find in the field is that the first thing that happens is people blame the pesticide. It's the pesticide that has now, let's call it, poisoned this person. And then, of course, the second thing is to blame the company that's manufacturing the pesticide. And together with that, blame the agro dealer who sold that pesticide for this overexposure incident. What we find in the field when we go out and investigate these issues is that in more than 90% of the cases, it's because of human factors that a person has been overexposed to pesticide, i.e. they didn't use the correct personal protective equipment, they were using the wrong dosages of the pesticide, they never read the label, etc., etc. And from company records, it's in excess of 90% of cases like this where it's a human factor that causes something to go wrong. What I want you to do is, as a trainer and as a person giving maybe a presentation to people involved with fall armyworm control, is use an example to try and illustrate this problem. So you can tell the audience, for example, you have a Toyota pickup. So on Friday afternoon after work, I decided to go and drink a beer while visiting with my friends. And then after I'd done that, I got in my Toyota pickup and I drove home. And on the way home, I had an accident, and there was a child playing next to the road that was killed because of this accident. And what you need to do with your audience is ask the audience where the blame lies. And I'll guarantee you that in 100% of the cases, your audience will say it's the person who drank too many beers and then caused the accident. They will never say it's the Toyota's fault. It's the person's fault. And I think this just, again, illustrates the way in which we see pesticides, because when a pesticide overexposure occurs, people blame the pesticide. And as I've already stated, in over 90% of cases, it's the human factor that does that. My wife likes to watch a TV program that we have here called, I think, Air Crash Investigation or something. In most of those cases, again, it's a human factor that causes a plane to crash. And one can debate these issues as much as you like, but that is the reality. So, as we said before, all pesticides are potentially harmful, but to make sure you are not exposed to excessive risk, you have to read them correctly. You have to be able to read and adhere to the label instructions companies go to a lot of effort to make sure that the instructions are clear and that you use the product in the correct way. It's not only the product that can be the issue, of course, it could be your equipment as well. And in the case of fall armyworm control in most of Africa, people will be using knapsack sprayers. And in the previous module, we illustrated some issues with knapsack sprayers. If you don't maintain your knapsack sprayer and make sure it's in good working order, that is potentially increasing your risk. And when that increases your risk, I'm sorry to say, it's not the pesticide that's at fault, it's the human being. Your personal protective equipment must be in place. And again, in module 1, we have illustrated how easy it is and to actually put PPE in place. One doesn't have to have fancy equipment that costs a lot of money and so on. For example, we looked at a thing of protecting your hands. How do you protect your hands? Yes, you can use a pair of gloves. What if gloves are not available? Cover your hands with a plastic bag. In the end, I think in most cases there is no excuse if these very simple steps are not followed and there are adverse reactions. In other words, overexposure or environmental damage or crop damage or loss. It doesn't help to blame a pesticide or a company. Most of the issues we have with these things are linked to human issues. So, what insecticides and classes of insecticides will we likely encounter when controlling fall armyworm in Africa? And the reality in Africa is that most of the insecticides that a farmer will have access to or will encounter in Africa are based on some of the older chemistries. These are normally cheaper than newer chemistries, but they, in many cases, not all cases, are potentially more harmful. As a trainer or somebody giving a presentation, you can ask people to try and list these pesticides so that one has an idea of what is available and what is going to be used in the area where you are doing the training. If you know that, then one is able to address issues related to specific active ingredients or insecticides. If you don't know what's available, you're not going to be able to help them to mitigate any hazards or risks. So most of the common pesticides available will belong to, in Africa, 3 main classes. It's the organophosphates and carbamates. Although those are 2 classes, their mode of action is very similar, so I've listed them together. And then the pyrethroids, these are probably the most common. And then a group of slightly newer chemistry called the neonicotinoids or the chloronicotinyls. They're also fairly widely available in Africa. And it'll be these 4 groups and 3 modes of action that most farmers will be exposed to or familiar with. So let's look at organophosphates quickly. Organophosphates are normally quite toxic compared to other insecticide classes, and you'll see a range of symptoms there that are typical of organophosphate or carbamate overexposure. Most of the labels that you'll encounter in the field will also have this kind of information on it, and information aimed at mitigating any of these symptoms. One of the other major classes of insecticides that will be encountered are the pyrethroids, and these typically cause a stinging or burning sensation on the skin if overexposed them. And this occurs also particularly around some of the mucous membranes like the nose, the eyes, and the mouth. And other symptoms include those that are similar to an allergic reaction, such as a runny nose, etc. And then the neonicotinoids or the chloronicotinyls will also, if exposed to them, will cause a skin or eye irritation. People can become dizzy. They can become, they breathe with difficulty, and they become confused, and eventually they might start vomiting as well. So All of these insecticide classes can cause a range of symptoms, and in many cases the symptoms between the different classes are very similar. So one must be aware of the fact that when somebody's overexposed and you do take them to a doctor or a clinic, that you do take the label with, because the label will indicate to the physician what class of insecticide this person has been overexposed to. So the next topic I want to discuss under this module is insecticide resistance. Once again, we have one of these slides here, which indicates to you as a trainer what to do and how to address this issue. Insecticide resistance management is a very complex topic with many concepts behind it that might be very foreign to farmers. An example of these would be, how would you describe, for example, fitness cost of resistance mechanisms in insects? It's very difficult to explain it to people like farmers and so on. So we've tried in the materials that you will see, the presentations and so on, not to explain these concepts in too much detail, but we've provided some videos. Some of them are from the Insect Resistance Action Committee, and a video that we've also created specifically for this project. And we've got a lot of links to information that you or farmers or people involved in fall armyworm projects can gather some more information in terms of insecticide resistance. You can also consult our website on the fall armyworm training materials at www.agritraining.co.za. Where all of this material and the links, etc., will be. One of the major sources of information is the IRAC website, and I would encourage you to go there and look at their materials and so on. Some of these materials we will show in the next couple of slides. Let's talk a little bit about insecticide resistance specifically in fall armyworm. In the original range where fall armyworm was found, in other words, South, Central and North America, there is abundant evidence of insecticide resistance in the species and to almost all chemical classes that are available for its control. We've also seen evidence that suggests that fall armyworm, when it first arrived in Africa a couple of years ago, the resistant genes were already present in that population that arrived here, and so those genes have then spread right throughout the continent. Fall armyworm has only very recently arrived in Australia as well, and in Western Australia, for example, they've already managed to identify the resistant genes in the fall armyworm population in Western Australia. So whether we like it or not, we already probably have resistance to a number of chemical classes within the fall armyworm population in Africa, and this must be managed from an insecticide point of view. As I mentioned already, the best source for information on this is the Insecticide Resistance Management Committee, and I've given you the link to the website there. IRAC is an industry body. In other words, it's made up of the agrochemical manufacturer companies, and they have a very nice fall armyworm poster about insecticide resistance in fall armyworm. There's a link to that as well there, but I will show that to you in the next slide. Okay, here is the IRAC resistance management poster for fall armyworm. One can download this from the website of IRAC, and we've also given you a link to it here. And you can print this as a handout if you're going to be training farmers, to give to them, to remind them about the issue, and as information for them. It's also possible to take this file, and it's a PDF file that one downloads from the IRAC website, and also print it as a poster, which you could use, for example, in an agro dealer shop, in an extension office, a building, places like that. One can print out the poster and put it up on the wall if you like, for people to see and to read. IRAC also have some very good videos related to insecticide resistance and the mode of action of various insecticide classes. So what we'll do now is we'll quickly run this video for insecticide resistance from IRAC. And again, we also give you links to these.
CropLife International and the Insecticide Resistance Action Committee explain how to combat insecticide resistance. This farmer is called James. He loves his job and is very proud of his produce. To avoid insect damage to his crops, James has always used the same insecticide and never had a problem. This year, James is worried because his crops are infested and spraying his fields does not kill many of the insects. If this continues, the whole harvest could be destroyed. James can't understand why the insecticide that worked so well before is not working so well now. An insecticide loses its effect because the insects have developed resistance to it. In any population of insects, there is genetic variability. The variability may give some insects a natural protection from this insecticide. If the same insecticide is always used, only insects that have this advantage survive. These resistant insects reproduce and pass on their advantage. Over time, this selection process fills the fields with resistant insects that are not affected by the insecticide. Luckily, there are other insecticides that have different modes of action. This means they attack the insects in different ways. Great, but how can we stop the process repeating and new types of resistance developing? Researchers carried out studies that show that by spraying insecticides with different modes of action in rotation throughout the crop growing season, the insects are controlled and the chance of resistance developing is greatly reduced. James can find information about what mode of action an insecticide uses printed on many bottles, online, or by asking the retailer. All insecticides with the same number share the same or a similar mode of action, so James makes sure to pick ones with different numbers. The rotation of chemical insecticides is an important element of an integrated approach to combating resistance, along with non-chemical practices like pest monitoring, crop rotation, soil tillage, and the encouragement of predators. James is delighted. By rotating insecticides with different modes of action and by implementing integrated pest management practices, he has solved his insect problem in a sustainable way. This saves him money by increasing his yield and improving the quality of his produce. James also finds he does not need to apply insecticide as regularly and has more free time with his family. Farmers like James are not alone in the fight against insecticide resistance. In urban environments, mosquitoes can also develop resistance. This increases the spread of malaria and has a huge impact on public health. IRAC works everywhere to combat the development of resistance. If you would like to learn more about insecticide resistance and the work of IRAC, visit the IRAC website.
This video also from IRAC will just illustrate to us what the different modes of action are of different classes of insecticide.
We explain the importance of using mode of action in insect resistance management. Bruno grows a range of vegetables on his farm, using insecticides to control pests. However, this isn't a simple task. Recently, one of the products he'd successfully used for a long time stopped being effective. The insects are now flourishing and destroying his crops. So Bruno speaks to his local agriculture advisor, Anna. She explains that insecticides can work in different ways. They can have a different mode of action. Repeated use of the same insecticide leads to insects developing resistance against that mode of action, making them hard to control. As a solution, Anna recommends an alternative product with a different mode of action to control the pests. She strongly advises Bruno to vary the insecticides he uses in order to combat resistance. This sounds sensible to Bruno, but how does it work? Insecticides can be grouped by mode of action based on their site of action within an insect. Prevention or management of resistance is normally achieved by varying insecticide modes of action during the growing season. This is known as rotation or alternation. Bruno could also use multiple applications of the same mode of action over a defined period of time before switching to another. This is typically around a month and is called a window or block strategy. Application windows are normally calculated based on the time it takes for the pest insects to develop and reproduce. This is known as generation time. With this information, Bruno visits his local retailer to buy the new insecticides. But he's immediately faced with a challenge. How does he find out what mode of action a product has? Retailer Zach explains that in many cases, insecticide products clearly display the mode of action employed, represented by a code. He shows Bruno 4 different insecticides for controlling aphid pests, each with a different mode of action. To prevent resistance, products with different numbers should be used. For instance, Bruno could begin with number 23, then switch to 9B or 1A for the next application. Letters after a specific mode of action indicate chemical and structural differences between insecticides that have the same mode of action. These should only be used for resistance management if no other insecticides with different modes of action are available. Zach reminds Bruno to always follow the manufacturer's label recommendations. Importantly, Bruno also keeps in mind that insects are mobile, so it's crucial to avoid products for which resistance has been reported in nearby areas. Zach encourages Bruno to work with other local farmers so they can share knowledge to help combat the threat of insect resistance together. In addition, Bruno discovers he can take other actions to control insects and reduce the cost of crop production. This is often referred to as Integrated Pest Management, or IPM. Using natural insect predators, removing old plants and rotating other crops that do not host the same insects are all ways to aid management. For more information on mode of action and resistance prevention, please visit IRAC-online.org.
So the 2 preceding videos from IRAC very nicely illustrated the management of insecticide resistance and the modes of action of different insecticides, and they refer back to topics that we've discussed in previous modules, such as integrated pest management, the use of natural enemies, crop rotation, all these type of things that help with insecticide resistance management. As a trainer or person involved in fall armyworm projects, you don't have to remember all this information because there is an app. So for any smartphone, there is an IRAC app that can be downloaded for free, and you don't have to then remember all these issues. You can search on this app for information regarding the various active ingredients. So this is just a picture of a Samsung smartphone with the IRAC app on it. And at the top there, you can see it says search for an insecticide. So all you would have to do is type your insecticide in there, and it will give you information in terms of the group and the mode of action of the insecticide. And in this way, you can educate farmers and other people in terms of insecticide resistance.
Insecticide resistance is a worldwide problem. In order to prevent it, it's important to first understand what exactly resistance to insecticide is and how it happens. Resistance to insecticides is defined as a heritable change in the sensitivity of a pest population that's reflected in the repeated failure of a product to achieve the expected level of control when used according to the label recommendation for that pest species. Let's take a look at this example. This is a susceptible moth that can be killed by a dose of 1 unit, and this is a resistant moth that can only be killed by a dose of 100 units. In any insect population, there will always be a few individuals that are naturally resistant to the insecticide. When spraying this population, these few resistant individuals will survive because no insecticide spray is always 100% effective on the susceptible individuals. Some of these will also survive. Therefore, the spray is assumed to be 90% effective. If we use the insecticide on this population, only 88% control is achieved. The resistance factor is 1. The surviving susceptible and resistant moths now breed and the population increases. This population will then contain a higher percentage of resistant individuals. If we use the same insecticide this time, only 76% control is achieved, and the resistance factor is 6 because more resistant individuals are present. When the survivors reproduce, there's more chance of resistant moths mating with other resistant moths. So this generation has a much higher proportion of resistant moths than the previous generation. Using the same insecticide spray in the third generation will only achieve 30% of control, making the resistance factor 22. This process is repeated every time the same insecticide is used. Resistant moths continue to multiply and ultimately become predominant in the population. Familiarize yourself with the basic principles like active ingredient rotational mixing, following labeling instructions, and many others to make sure that you manage resistance successfully. Once resistance reaches a certain level, it will be difficult to contain.
I think the main message about combating insecticide resistance, specifically for fall armyworm, is that every single time we use an insecticide spray against fall armyworm, we must rotate it to a different chemical class. We know that these moths are already resistant to a number of chemical classes, so we should actually rotate every single spray. I think something that came out of the previous short animation as well is that you must remember from module 2, I think it was, where we discussed the biology of this pest, its generation time is something in the order of maximum of 3 weeks under the right conditions. So what is happening is this cycle of spraying resistant individuals, breeding and so on, is happening every 3 weeks. And because the life cycle is so fast, insecticide resistance can develop very quickly in an insect such as the fall armyworm. And it's not only the fall armyworm that's like this. Many insects have very short generation times and resistance can develop very quickly. If one were to sort of compare this to human beings, and let's assume for a moment that human beings were pests and we were spraying them, they would have the same, the effect would be the same, because there will always be a few individuals in the human population that will also be resistant to whatever we're using to spray them. And those individuals, like with the moths we just saw in the previous video, would then again breed, and we would have more individuals that are resistant in the population. But what one must remember is that the generation time of a human being is something like 20 years. So this process would be very slow, whereas in insects it can happen very, very fast. So we'd like to encourage extension officers, trainers, farmers to rotate their insecticides when spraying for fall armyworm every single time if possible.